All right, so today what we're going to look at is differentiability, which is a great word if you can do it in Scrabble because it's got a lot of letters and opens up all kinds of things. So remember that if the right-hand derivative at c is not equal to the left-hand derivative at c, then the derivative at c does not exist. And there's lots of different ways that this can happen. So for example, on this one, this is typically called a corner. Some books call it a sharp corner. I usually just say the left-hand derivative at c does not equal the right-hand derivative at c. Yes, it's more words than writing corner, but it's more mathematically correct. At this point, the latest I heard is that on the AP exam, they're still accept saying that this doesn't have a derivative because it has a corner in the graph at x equals c. But there are rumblings amongst the people who do these things who are like, yeah, we're not going to take that anymore. So again, I would just say that the left-hand derivative and the right-hand derivative at x equals c are not equal to one another. Closely related to that is an idea of a cusp. To be a true cusp, these both have to be curves such that both of them have a vertical tangent at this point in between these two pieces. Okay, that's called a cusp. You can also have a vertical tangent that looks like this. Now, what's the problem with the vertical tangent? Well, the problem over here is that the derivative over here on this left side, as we're coming from the left, looks like it's probably about like that. The derivative on the right side looks like this. Those aren't close to being the same slope. For the cusp and for the vertical tangent, you're like, well, yeah, that is a perfectly good tangent line. Why isn't the derivative? Why doesn't the derivative exist at that point? Well, what's the slope of a vertical line? Yes, it's undefined. And since the derivative is the slope, the derivative is undefined here because it has a vertical tangent line. The other place that you're going to have no derivative at a point is any place you have a discontinuity, and it doesn't matter what kind of discontinuity it is. Here I'm showing you a jump discontinuity, and I'll show you what the problem is. Over here, the slopes are all like this, right? They're all 0. Over here, when I connect this point to this, what kind of slopes am I getting? What kind of a slope is this? It's not 0. It's a clearly positive, and if I move this point down here closer to the hole, it's going to become closer and closer to a vertical line. That's what happened on that very last problem on the homework, is that the derivative, I think it was the last one on the homework, the derivative from one side was a nice number, and the other side, the limit just doesn't exist. It had a discontinuity like this one. So we get to a theorem here that students aren't always as careful of as they ought to be. It says differentiability implies continuity. So if a function has a derivative at x equals a, then it is continuous at x equals a. And I wrote down here the converse is false. It's not really that the converse is always false. It's the converse isn't always true, therefore it's false, if you take my meaning. Just because a function is continuous at a point doesn't mean that it has a derivative at that point. But if we know the function is differentiable at a point, We know that it's continuous at that point. You'd be surprised how many times this idea comes up buried in some piece of a free response question on the AP exam, where they tell you that the function is differentiable, and in order to prove something that you need to prove, you need to say that the function is continuous. Now, this second one, differentiability implies local linearity. Basically, that means that if f has a derivative at a, then if you were to zoom in on that point, it would look like a line. In fact, it would closely resemble its tangent line. Let me show you a picture of that on a graph. So this is the graph of, I think it's 1 over x. Yep. And this is its tangent line at 1/2. It looks like this. If I was to zoom way in on this, and I don't know if have you guys ever done a zoom box? I'm taking that as a no, since no one raised their hand there. With a zoom box, you know what? Let me change the window first so I can see the. Let's do a zoom standard to start with. And the point I'm interested in is right in here. Yeah. So what I'm going to do is a zoom box. And what you do is, let's say I want to start at 0, 0. I just hit enter. And then I move to one side and up or down. And now everything inside of this box is going to now fill the screen. So there's my 1 over x. And there's my tangent line. So I'm going to do another zoom box. And I'm going to zoom way in on this. So you just set one of your corners, and then you go set the opposite corner. So there's 1 over x, and here's my tangent line. Yeah, they're pretty close together. You see how this 1 over x is starting to look more and more like a line? And in fact, it's starting to look a lot like this tangent line. Let's see. If that's 1 over x and it's at 1, hang on just a second. Let me find a place where I can zoom in on this well. Let's see, where do those two intersect? Uh-oh, I think I broke it. Every now and then, yeah, it's just barely skating it, and it's not finding the place that it intersects the way that it wants to. Well, anyway, I've spent more time on this than I wanted to. The idea is that if you zoom in on it enough, the curve starts to look like a line, and it's impossible to tell the difference between the line and the curve. Okay? All right. So intermediate values and derivatives. We did the intermediate value theorem the other day. And we can apply it to derivatives also. If a function is differentiable on an interval, then the intermediate value theorem applies to the derivative on that interval. So that means that if a and b are any 2 points in an interval for which the derivative of the function exists, in other words, f is differentiable, then f prime takes on every value between f prime at a and f prime at b. It's just handy to know that sometimes. Okay, so numerical derivatives. We have already kind of done this when we were estimating the instantaneous rate of change by putting in a point very close to the to the point where we wanted to find the instantaneous rate of change. So for small values of h, the difference quotient f of a plus h minus f of a over h gives me an approximation for f prime at a. However, for the same value of h, we will usually get a better approximation if we use the symmetric difference quotient, f of a plus h minus f of a minus h all over 2h. Let me show you what's going on there. So on this, here is f of a. And let's say that I make h be about like this. So this is a plus h. So if I was to connect these 2 points, let me use a different color. Looks sort of like this. Do you see how that's not quite tangent to the curve? It's actually a little bit below the curve over here. And I tell you what, I'm going to make that further away so that you can see it. I'm going to make h bigger. So let's make this a plus h way the heck over here. So this is going to be f at a plus h. And this will be f at a. All right, now can you see that that's not really tangent to the curve at that point? Okay, it's too small because this curve is curving downwards. If we went the same distance over here, though, and did another point, what we would have is we would have, I'm going to do this in a completely different color, a point over here and a point, say, over here, the same distance away. Do you see how that is pretty close to being the same as the slope of the tangent? So if we just go to one side, we're not as good. If we go a little bit to one side, a little bit to the other side, and then we have to divide by 2h, we tend to get a better approximation. Now, this is an okay approximation, and sometimes this is all we can do. But if we want a better approximation, we can use this one. All right, so at this point, I think I told you guys the other day, there are 4 things that you have to be able to use your calculator for on the AP exam for calculus. 1 is to be able to graph something in an appropriate viewing window. Second thing is to be able to solve an equation. The third thing is to be able to take a numerical derivative. And here's how it works. If you're trying to estimate the derivative of f of x is equal to x to the 4th at 2, you could do that by using a really small value of h and doing f of 2 plus h minus f of 2 over h and get an approximation. But your calculator will do that all in one step for you. So if you've got your calculator, grab that. If you go to the math menu, scroll down to number 8. The N there is for numerical and deriv, obviously for derivative, the numerical derivative. So I want to take the derivative with respect to the variable, which is x, of x raised to the 4th. And this vertical line here is called an evaluation bar, which is going to be the name of the pub that I'm going to open after I retire. Just kidding. Man, this is a tough room. At x equals 2. Bada boom, bada bing. To 3 decimal places, this is perfectly accurate. F prime of 2 is approximately equal to 32.000. It's actually exactly 32 as it turns out, but we don't know that. Now, I want you to notice, if I used that symmetric difference quotient, I would have gotten the same thing. Remember, and if I had done that for 1/1000th, so if I did f of 2 plus 0.001 minus f at 2 minus 0.001 divided by 2 times 0.001. So that's the change in y over the change in x. So when they get ugly like that, I like having a horizontal fraction bar. Ooh, that'd be another good name for a pub. And that's going to be cubed, to the 4th rather, minus 2 minus 0.001 raised to the 4th, all over 2 times 0.001. I guess I don't need parentheses there. It's exactly the same number. This is actually what your calculator is doing in its little pea brain, is it is going 1/1000th to one side, 1/1000th to the other side, and finding the slope. Okay? So, let's let f of x be equal to the natural log of x. Here we're going to use the numerical derivative to graph y prime of x. And then we're going to try to guess what the function for f prime of x is. Well, that should be fun. How do we do that? Well, we go to y equals, clear out this stuff. So I want the derivative of natural log of x. So I'm going to go math 8. I want the derivative with respect to x of the natural log of x. And this is the only tricky part, is right here at the end. Where do we want to evaluate? We don't want to evaluate it at just one point. We want to evaluate it at a whole bunch of points. So what we're going to do is tell it to evaluate at x equals x. In other words, wherever it is horizontally, we want it to use that x value to approximate the derivative. And we'll go back to a zoom standard. And it's pretty tough to guess what that function is just by looking at it. So let's go to the table. I need to get back to 0, and I don't feel like scrolling up, so I'm going to do a table set. Start at 0 and go by ones. So at 1, the derivative was 1. At 2, the derivative was 0.5, which as a fraction is what? Yep. And then 0.333, what is that? 1/3. And 0.25. And 0.2. Anybody want to guess what 0.16666 is? So when x was 1, the derivative was 1. When x was 2, the derivative was 1/2. When x is 3, the derivative is 1/3, etc., 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 etc. So what do you think a function for f of x would be? So I'm not telling you this one because this is actually pretty simple, guys. You're making it harder than it is. This is the derivative, remember? So thank you. Be brave, everybody. Yeah, it's 1/x. How can we verify that? Well, graphically, let me get rid of this stuff on my screen. If I go back to y equals, and I put 1/x here, and if it traces right over it, I'm not going to be able to see it very well. So I'm going to go back over to here, and not just make it thick, but I'm going to make it, if you hit it 4 times, you get this little ball, and it's going to show as it traces it. So graph. There's my derivative. Here comes 1 over x, and you're like, wait a minute, I don't have a derivative over here. But watch it over here. Why didn't I have a derivative over here? What do we know about natural log of x? What is the domain of natural log of x? Yeah, except it doesn't include 0. You were close. Natural log of 0 doesn't exist. But natural log of anything positive, so the derivative is 1 over x for x greater than 0. Okay, any questions about that? Who came in? Ah, okay. All right. Well, if the bell is rung, then you guys have a good day, and I'll talk to you later.